Last part we finished up the L3VNI configuration and we had access between devices in the same L3VNI. We tested some access in some servers between VLAN 10 and VLAN 20. So the next layer on top of that is allowing access between L3VNIs, so allowing access between VLAN 10 and VLAN 20 from an IP, a layer 3 perspective essentially. So what we need to do for that is we need to configure kind of a tenant VRF, an L3VNI, and then we need to put some Anycast gateways on the leaves so that we've got essentially a distributed gateway across all the leaves, so that it's always a local gateway for the leaves. They don't have to go to some border leaves to get to their gateway. It's always going to be local, which is a bit more efficient, which is one of the perks of being able to use something like VXLAN EVPN. So we will do that first. So again, this is configuration just for the leaves. But we will configure the Anycast Gateway MAC address. So this is a shared MAC address that we configure across all the switches that essentially sets the MAC for that Anycast Gateway SVI that we create. So we'll get everyone into configuration mode. The good thing about this is that we're able to essentially set it the same on all the leaves. So if, for example, you had something like vMotion or Live Motion and you were moving virtual machines between servers that were connected to different leaves, the MAC address for the gateway wouldn't change when this VM moved to a different set of leaves. It would always be the same. It wouldn't have to re-ARP for the gateway, and it wouldn't it'd have less of a connectivity issue when it came up on the other leaf. So what we need to do to configure that is say fabric forwarding Anycast Gateway MAC, and we'll use all A's, all B's, and all C's, and we'll configure that on all of the leaves. None of the configuration that we're going to do here is applicable to the spines. The spines are kind of not oblivious to it, but they're just they're not terminating any of this traffic, they're just forwarding it. So we'll do that first, and then so by way of set up an L3VNI we need a new VLAN for it essentially. So what we'll do is we'll create VLAN 999. We have to set a VN segment for it, so we'll say 100.999, and we'll create that on all of the leaves because the L3VNI has to live on all the leaves. Perfect. And then we need to create a VRF. So essentially, for a multi-tenant environment, you would have multiple VRFs, and we are going to look at multi-tenancy at the end of the video with how we can split that out. But for one tenant, all you need is one VRF. So we'll create a VRF, and we'll call that overlay tenant 1. We have to set a VNI within there as well, so we'll use the same as this, which has to match essentially because this is how we're calling, which is how we're essentially attaching those two together. We'll say RD auto, we'll come into the address family of IPv4 unicast, and we'll set the route target for both to auto, and we'll also add the EVPN keyword onto the end of that. And if you don't know, the way that the RD auto and the route target auto work is they take the autonomous system number colon then this VNI. So we should see that with, at least with the route target, we should see that in some of the routes a bit later on. You can set it statically if you want, or manually if you want, but it's sometimes just a bit easier to set it as auto because it's quite predictable anyway. If we do show run VRF, and then grab this, got to put this on all the other leaves as well. I've seen this before. For some reason it gives you, when you do show run, it gives you the VNI last, but it wants it before because it can't set the route targets without it. It's a bit backwards from Cisco, but we'll get that on all the leaves. And then this does need its own VLAN, its own SVI, so int VLAN 999. It doesn't need an IP address, it just needs no shutting, we need to say it's a member of this VRF, and then we just say IP forward, IP route IP forward. So it hasn't got an actual IP address. So show run interface VLAN 999. Again, it wants to be on all the leaves, same as all the VXLAN initial setup. It's very repetitive. Cool. And then last but not least, we have to associate this within the VTEP. So interface NVE1 member VNI was 100.999, and we have to say associate VRF, and that essentially says I am an L3VNI. We'll do that again on all the other leaves. That should be it for the L3VNI itself. Perfect. And then now we can actually create the Anycast gateways, because essentially the Anycast gateways need to be part of this VRF. So we could create them first, but you'd have to, you know, put the IP back on it anyway, because once you change the VRF on a layer 3 interface, it strips the layer 3 configuration off it, so it doesn't really make sense. So interface VLAN 10, we will now shut it. We will say that it's a member of this VRF. We'll give it an IP address, so IP address is 10.1.1.254, and it's a /24, and then last we have to say fabric forwarding mode is Anycast gateway, so we have to specifically call out that this is an Anycast gateway, and that's what assigns it the MAC address and other bits and pieces. We'll do the same for VLAN 20, so again we'll now shut it. It's part of the same VRF. We will give it the IP address for that for that VLAN, and then we'll say it's an Anycast gateway. And then let's just grab this config together so we can get it on all the other leaves, and I'll remove the stuff in between, like so. And then that should be it for the configuration side of things that we need to do for the second. Cool. If we do a show interface status, we should see, yep, our two SVIs are connected, which is a good sign. Let's have a look on a client. So this is server 1 VL10. Can see its IP address, its gateway is .254. We should be able to ping that now. So ping 10.1.1.254. We can ping that, that's a good sign. I don't think... No, I don't have ARP on here, and I can't install anything because I haven't got any internet. If I cat procnet, I think it's ARP. Yes, there we go. So we can see in here that we've got 10.1.1.254, and the hardware address for that is the Anycast gateway MAC address that we set, and we can see the device for that is Bond 0. From a VLAN 20 perspective, we can see we're 10.2.1.1. If we do a ping to 10.2.1.254, we should see, yep, we've got pings on that. And if we do the same, so cat procnet ARP, we can again see that we have got all A's, all B's, all C's. That's a good sign. So, if we've done everything right, we should actually be able to ping between these two devices, or these two servers. So this is 10.2.1.1, ping 10.2.1.1, and we can. So that's proving now that we can ping between VLAN 10 and VLAN 20. I don't think I can do a trace route either, because I don't think it'll be installed. No. Helps if I spell it right. Yeah, no, it's not installed either. But essentially, it will be the exact same as any normal any normal trace route with VXLAN where you'll see the gateway twice, because you'll essentially see it once for its local gateway and then twice for its remote, and then you'll see it hit the actual device. If we want to jump off this leaf, because at the minute we're just pinging between these two, so let's say we can ping from server 1 to server 6, so server 6 will be 10.2.1.3, so if we ping 10.2.1.3, we can see that we can ping that, and we can see the latency is a bit higher, showing it, using more of the infrastructure, which is good. So from a verification standpoint, if we look on leaf 1 and do a show IP route for overlay tenant 1, so this is the IP routing table. We can see that we've got attached routes in here. We can see that we've got a couple of /32s, or we've got a few /32s. This is a /32 route for a non-local VLAN 10 client. We can see that it's via that VTEP, and we can see that it's encapsulated in VXLAN. So now that we've got these /32s in here, we can see that we've got /32s for VLAN 10, and down here we've got /32s for VLAN 20 as well. So that's how the routing under the hood is working. So it's essentially created this VRF for us, and we've now got these /32 routes in here. We've still got the L3VPN EVPN routes. So if we have a look on the spine, BGP L2 VPN EVPN, we can see on here that we've still got all those existing routes. However, if we look on leaf and actually do show BGP L2 VPN EVPN, and we have a look at something remote, so if we have a look at 10.2.1.3, which is the device that we just pinged from server 1, if we have a look at that, so we'll see, because we've still got the L3VNI, if I come right down here, we'll see that we've got all of the routing information for the L2VNI, which is within that L3VNI, which is 1020. That's all fine, because that's the bridging side of things. But if we keep scrolling down, at some point we will see, here we go, L3VNI. So this is the L3 side of things. So this is what's populating that routing table, and we can see pretty much the same thing. We've got the originators are leaves 5 and 6, so we can see that with 7 and 8. We can see that it's come via the cluster list of .1, which is spine 1. It's got everything that we'd expect. It's got the site of origin, and this is also where we start to see the router MAC. So this, if we looked on leaf 5 and 6, if we did that show NVE interface, NVE1, I think it's detail, yeah. So that there should be the MAC address that we see there, which it is. So essentially what we're going to do is when we send this traffic to this next hop, which is the secondary address on loopback 1 of leaves 5 and 6, when we send that traffic to that VTEP, the destination MAC address will be this, so that it knows that it's destined for the NVE interface. And again, that is the shared MAC address between the two vPC peers, rather than it being a specific MAC address of one of them, because it's a port channel, and the hashing algorithm in theory could allow that traffic to go out of either link. So we can also see a bit more information on these routes. We can see that it's got 2 extended communities. Well, I mean, really it's got more, but it's got 2 route targets. So we can see there's a route target for the L2VNI, which is 1020, and it's got a route target for 10999, which is the L3 side of things. So we can see that this has definitely come through into the L3VNI. We should actually be able to see on the, where are we on leaf 1, so we're .3 on the L2VNI side of things. In fact, it'll be where it says, here we go, imported to 3 destinations. So this is .8, so this is the leaf 6 VTEP. So this is the route distinguisher for that, and we can see that these were designated as best because we can see this is imported into 3 destinations. it's been imported into the L2VNI, it's been imported into the L3VNI, and then it's been imported into our overlay tenant 1 VRF. So we can see that there. We can see it there as well. So one, obviously with Cisco BGP's best path algorithm, we can see that one route has been picked out of each route distinguisher of the devices this is connected to. So there's one for leaf 6 and there's one here for leaf 5, and we can see that the best path in both of those has been imported into 3 destinations, which we'd expect. So that's how the routing is working under the hood. So now if we wanted to look at something that splits these apart, so some multi-tenancy, we can actually kind of split VLAN 20 and VLAN 10 apart and have them in 2 separate VRFs. So say you were a service provider and you had one big shared fabric, but you wanted multiple customers to use that single fabric but be isolated from a layer 3 perspective. This is where you would have multiple L3VNIs and multiple VRFs. So what we're going to do now is we'll split the L3VNIs out. So we've got VLAN 10 to stay in 100.999, and we'll have VLAN 20 move into 100.998. So in order for us to do that, we need to change the configuration essentially on all the leaves. So we need to create a new VRF, create a new VLAN for the L3VNI, and then essentially do all that configuration just duplicated again. So let's come back into configuration mode. We'll create VLAN 998, set the VN segment for that to 100, 998. We'll create a VRF context of overlay tenant 2. Set the VNI to be the same as the VLAN. Set the RD to auto. Address family of IPv4 unicast. We'll set the route target for both to auto, and then we'll also add that the same for EVPN. We also need to, in interface NVE1, we need to say member VNI. We also need to associate the VRF of this one, again saying that we are an L3VNI. We need to create an SVI for VLAN 998, so int VLAN 998 no shut VRF member of overlay tenant 2, and then IP forward. And then now, because we've moved it, we need to also actually configure interface VLAN 20. Let's just do a show run interface VLAN 20, because what we need to do is we need to change the VRF member of this to be tenant 2, and as soon as we do that, it'll remove this configuration. So we'll put that back on. Cool. So we've created a VLAN, a layer 2 VLAN. We've given it a VN segment. We've created our new VRF. We've set the VNI within that VRF. We've added the VNI to the VTEP and said associate VRF, which is essentially us saying this is an L3VNI. We've created the SVI for VLAN 998, and then we've moved VLAN 20, which is the the sort of VLAN that we're going to move away into a separate VRF, and tenant into that tenant VRF. So we need to do the exact same configuration on all the leaves. So if we show run VLAN 20, so actually show 998. Show run VRF overlay tenant 2 NVE1. So copy copy all that, and then just make this so it's all one continuous piece of configuration. Need to move that to the top, or middle top. So yeah, we're creating our VLAN, we're creating our new VRF, we're adding our SVI, we are adding, we don't need that because that's duplicated, and then we're associating it with the NV interface. We do still need to add or change the VLAN 20 SVI, but we can do that afterwards after we've got this configuration in. We're not in configuration mode there. Cool. So if we show run interface VLAN 20, oh, that hasn't moved yet. Let's do that on leaf 1. Then just copy this onto all of our leaves, and I'll just essentially recreate the VLAN 20 Anycast Gateway and move it onto the new tenant VRF. Cool. So last thing we need to do is within BGP is we need to advertise the subnets for each VRF essentially. Well, in VLAN 10 or in overlay tenant 1 we need to advertise VLAN 10. In an overlay tenant 2 we need to advertise VLAN 20. So let's just check our BGP configuration as it is. Yeah, so we need to add the VRFs into there. So router BGP 64500 VRF overlay tenant 1 address family of IPv4 unicast, and we will set network as 10.1.1.0 mask of /24, and then we'll come into the other VRF address family and then we'll advertise the other one. So if we just check that out, we'll grab that and just remove this so we've got just the configuration we want. So this will essentially put a bit of a catch-all route into BGP to allow anything that's not necessarily known to be routed to the VTEPs. So if we do a show IP route for VRF overlay tenant 1, we'll see that now we've only got 10.1 things in there, and if we do overlay tenant 2 we can see that we've only got 10.2 routes in there. And what we should have essentially done in doing that is, whereas before on this server, which is server 1 in VLAN 10, we were able to ping between VLAN 10 and VLAN 20, we should now no longer be able to do that, and we can't, which is a good sign. But what we should still be able to do is we should still be able to ping everything in our own VLAN, and we can ping .3, we can ping .2, and we are .1. So what we've essentially done by segmenting these VRFs off and creating the other L3VNI is we've essentially isolated tenant 1 and tenant 2. Yes, they're sharing the same fabric, yes, they're sharing the same underlay, but they are, on an overlay perspective, they are separate. They're in their own separate VRFs, in their own separate routing table. So essentially we will double check that VLAN 20 is still functioning as intended. So we can still ping .1, .2, I think we are .2. .3 works. So everything there works, but we shouldn't be able to ping. We shouldn't even be able to ping the the Anycast Gateway of the other, because it's not in the routing table. If we looked, server 2 VL20 is connected to leaf 2 and 1, but if we looked on these, and we've already seen in here that that is the routing table that it would come into because it's in this VRF, and there's nothing in there associated with 10.1. There's no default route, there's no catch-all route, there's nothing in there. So it's not that we're blocking the traffic, it's that there's no route for it. It's layer 3 separated. So to kind of accompany that, let's say that don't know, you've got again a service provider, and you've got two tenants which are doing a company merger, for example, and they now want to be able to communicate with each other. So what we can do now is, instead of having to move all of, say, company B's SVIs and L3VNIs into one big VRF, we can essentially leak routes between the VRFs and allow them to communicate between the VRFs. You can also do this if you've got like a shared services VRF. So say again you're a service provider and you've got like DNS services or some domain services in its own VRF. You can essentially allow access to that by doing this, by doing what I'm about to show you. So the caveat with this is we've got to essentially elect some border nodes, or some border leaves as they're called. So these border leaves are going to be the ones that are responsible for doing that route leaking. So it's not going to be done on every single leaf, it's going to be done on specific leaves. And in this scenario we've got VPCs, so we're going to need, we've got VPC peerings, so we're going to we've got VPCs, so essentially we need to elect two border leaves, because it would make sense to, for example, not just have leaf 3 be a border leaf, but have leaf 3 and leaf 4 be a border leaf. So that's exactly what we're going to do. Leaf 3 and leaf 4 are going to be the border leaves, because later on they're going to connect us out to the internet using an external firewall. So essentially we need to configure leaves 3 and 4 to leak between those two VRFs. So if we have a look on them at the minute, we should be able to see the exact same as any other leaf. So IP route VRF overlay tenant 1 and overlay tenant 2. We've got two separate VRFs, and we essentially need to allow leaking from one to the other. But what we also need to do is we need to configure some way of telling the other leaves how to get to them, because what we'll see when we leak things is that the routes don't automatically get advertised. There's certain things you have to do within the VRF to do that, but what we can do to be smarter is we can create some summary addresses so that we're attracting the traffic to the border leaves without having to send all the routes to all the leaves, and essentially having two bigger routing tables. So it's just a bit more efficient doing it that way. You can do it with a default route, which I think I have shown in the past. However, in this case we're going to use aggregate addresses within BGP to essentially advertise a summary. So what we need to do is, on leaf 3 and 4, come into router BGP 64500. No, help if I'm in configuration mode. There we go. Then we'll come into the VRF for overlay tenant 1, address family of IPv4 unicast. And where we did just configure the networks in here, what we want to do now is we want to say aggregate address, and then because we're in tenant 1, so what we're going to say is, for example, tenant 1 is 10.1/16 and tenant 2 is 10.2/16. Say they're the ranges that they've been assigned by us as the service provider. So what we want to do is we want to tell tenant 1 about tenant 2's subnets. So what we'll be doing is we'll be creating an aggregate address within the tenant 1 VRF for the tenant 2 IP space. So we'll say 10.2.0.0/16, and then we'll also say summary only, because we only want to send the summary. It doesn't make, if we're trying to be efficient about it, it doesn't make sense to send the summary and all the individual routes. So it's just a bit of a no-brainer. So tenant 2 unicast, and then we'll do the exact same thing, but we'll just advertise essentially tenant 1's IP space. So we need to do the exact same thing on leaf 4 because it is also an elected border leaf. I think I'm already in BGP, but just for good measure, VRF overlay tenant 1, address family IPv4 unicast, IPv4 unicast, and then aggregate address for 10.2.0.0/16, summary only, and then tenant 2 we'll do .1. So the way that aggregate addresses work in BGP is that these won't be advertised unless there is routes within. So if we did a show BGP VRF overlay tenant 1 IPv4 unicast, we will see that we do see the A for aggregate, but it hasn't got a valid or a best flag next to it. And the reason for that is there are no routes within that supernet, if you want to call it that, to allow BGP to advertise that as a subnet. We'll see the exact same thing for tenant 2, but that we can see the aggregate there, but it's not being advertised because it's not best, or it's not valid, so to speak, because that is the validity identifier, and it's saying it's not valid. So as soon as we do the tenant leaking between the VRFs, we'll see that gets advertised because we'll start to see routes within that supernet appear in these tables, and that's what triggers BGP to say, right, I can advertise that. So in doing that, in talking about that, let's do that. So the way that the so if I do a show run VRF overlay tenant 1, so the way that this RD auto works is, well, in fact it's the root targets that we're going to use anyway, but the way that the root target works is it takes the ASN colon and then the VNI. So for all intents and purposes, the root target for this VRF is 64.500 colon 100.999, and then for overlay tenant 2 it's 64.500 100.998. So what we need to say is, if we come into VRF context overlay tenant 1 address family of IPv4 unicast, we want to say root target, and we want to import because we're importing into this VRF, and the root target we want to import is 64.500 colon 100.998. So that's us saying that I want to import routes from this root target. That root target matches the root target for the overlay tenant 2 because its VNI there is 100.998 and the ASN is 64.500. So we say that, and then because we're dealing with EVPN routes as well, we need to add the EVPN onto the end of that as well. Likewise in the other VRF, so overlay tenant 2, we need to essentially do the exact same thing, but instead of 10 or 100.998, we need to say 100.999 and then EVPN as well. And then if we do a show run section VRF, we'll see now that we've got these two commands in there. We need to do the same on leaf 4, so VRF context overlay tenant 1 address family of IPv4 unicast, and then root target import. So we're in overlay tenant 1, we want to import 64.500 100.998 and the VPN routes, and then tenant 2 we want to do the exact same but for 100.999. Perfect. So pretty much immediately what we should be able to do is on leaf 3 do a show IP route VRF overlay tenant 1, and we'll see there's a lot more routes in there. So we can see now that we do have there it is, we do have the /16 in there now. We've also got a /24 or the /24 from the other VRF. We've also got a couple of /32s there. So we're looking at the route table for overlay tenant 1, which it should be 10.1, but we're now seeing, because we've done the route leaking, we're seeing 10.2 routes in here as well. and we can see that we can get to those through overlay tenant 2. You can see by this little % sign and then the other VRF essentially, which it's telling us to use if we want to get there. So if we do something similar for overlay tenant 2, we'll see the exact same. So overlay tenant 2 should have just been 10.2 routes, which we can obviously still see down here, but we've got now the 10.1 routes in here. We've got the 10.1/16, and then we've also got a couple of /32s and our /24, which is the specific subnet, so to speak, that we've got configured. So if we look at leaf 1, for example, so this is a non-border leaf, and have a look in here, we can see, and this is where I was talking about having just the summary. So now that we've got just the summary, we've got much less in the route table. We don't necessarily need to know that this specific /32 is available via the border leaves, because it's all going to end up going there, so we may as well advertise just a summary address. So hopefully what we should be able to do is jump back to a server. So this wasn't working when we were trying to ping between, so just to verify IPA, we are 10.1.1.1. If we try pinging 10.2.1.1, we can see that now we've got connectivity with that, whereas we didn't before. We should have connectivity with .2 as well, and .3. So that's showing now we've got full connectivity back between VLAN 10 and VLAN 20. I'll confirm that on a VLAN 20 server by pinging 10.1.1.1. See, that's working. 10.1.1.2. That's working, and 10.1.1.3, and that's working. So that traffic will be going up to the, say we were going between this server and server 6 down here. That traffic will be going to leaf 1 or leaf 2, depending on the way that the hashing algorithm works, but it'll use one of these two. It'll route across using either spine to the border leaves, so 3 or 4, and then those border leaves will send that traffic back to the destination on leaf 5 and 6. So yes, it's slightly less efficient in that it's going to have to, the traffic, even if it was between these two servers here, it would still have to use the border leaves, but that's just the way, because they're in separate tenants, that's just the way that, you know, we best do it. You could have more border leaves, but it starts to get more complex with where you're advertising the routes, because essentially everything in here is using iBGP, so you can't really easily mess with the path selection without having to start changing metrics and things like that, which it's just easier from a design perspective to have a set of border nodes like we've got here with leaf 3 and leaf 4. So there isn't really much else to sort of show. It's working. We can see the routes. It might be worth having a look on here, because what we should be able to see now, so whereas before all we were seeing was type 2 routes, which are either MAC addresses or MAC addresses and IP addresses, we can now see that we can see some type 5 routes, which in EVPN that essentially is an IP prefix route. So you can see this one here is a type 5 route, and it's a /24, and it's for 10.2.1.0/24, and that is essentially a I suppose you could kind of say it's a standard BGP unicast prefix, just encapsulated within VXLAN. That's kind of the way that BGP advertises those, which is quite cool. We can have a look at that specifically as well, and it'll give us more information about it, where it's come from, and where it's been advertised to, because we're on the route reflectors. It's been advertised to the all the leaves, apart from the ones that it came from. So yeah, in the next video we'll have a look at getting some access outside of the fabric, but for now we've enabled multi-tenancy, and we then join them back together so that you can essentially have multi-tenancy with communication between. So I just wanted to show a couple of extra little bonus bits on this with the configuration that we've just done. So if I do a show IP route for VRF overlay tenant 1, we can see that the route that we've got that's for 10.2/16, we can only see one next hop for it, or yeah, one next hop for it, which is 10.0.1.3, which is leaf 3. But we've got two border leaves in theory, so we should see two routes there. The reason for that is BGP's default configuration, at least on Cisco Nexus, is that it only ever gives you the best path. Even if there are multiple paths that are exactly the same, you have to essentially enable a feature called maximum paths and increase it from 1 to whatever number you want. So what we'll do to change that is if we come into routes BGP 64500 and we come into the address family of IP, actually now we VRF overlay tenant 1 and then the address family of IPv4 unicast. If we say maximum paths and then we get a few options, we get EIBGP, which is for both eBGP and iBGP, and then we get iBGP. We are in an iBGP fabric, so we can specifically call out iBGP, and then it essentially asks us for a number between 1 and 128. So we want, 2, we've got two border leaves, so we may as well say 2. If we then also come into the other tenant VRF, address family IPv4 unicast, and say the same thing, if we now look at our routing table, we can see that now we've got two paths. Instead, before where we had one path, we've now got two paths to the /16 for the other tenant. So now we'll do equal cost multipath to both border leaves instead of just sending it to one, and then if that one were to fail, we could fail back. It's better to have load balancing and fault tolerance than just fault tolerance, I suppose.